This question has a little bit of everything. It talks about the binomial being approximated by a normal. It states, you have to write down the conditions under which you can approximate a binomial using a normal. And then it goes through and does a hypothesis test as well. So there's a kind of a little bit of everything thrown in here. What it doesn't have is the hypothesis test where there's a sample size, unfortunately, but can't fit everything into one session really. So let's get started. First part of the question is state the conditions under which the normal distribution may be used as an approximation to the binomial distribution. And this is a pretty standard kind of 2-mark question. The reason it's 2 marks is that there are 2 conditions that we are aware of and need to be aware of. So the first condition for when we approximate a binomial distribution using a normal distribution is that there are a large number of trials. Okay? Now, this idea of a large number of trials, there's no set number that you need to be looking out for. It's quite subjective, really. But I'll explain once we've written down the second thing how it affects the approximation. So there needs to be a large number of trials, okay? Something kind of unwieldy to work with, I would say. So there needs to be a large number of trials. The second thing is that the probability of the success, which is what we look at with a binomial distribution, so we say the probability of success needs to be close to 0.5. Now, again, that's pretty subjective, right? What is close to 0.5? What you decide is close to 0.5 might be different to what I decide is close to 0.5. But here's how these 2 actually work in real life, right? It's not just a case of memorizing these. The reason these work is the larger the number of trials and the closer the probability of success is to 0.5, then the more accurate the approximation will be. If you reduce the number of trials and the probability gets further away from 0.5, then the approximation becomes less accurate. And that's how these 2 things work, all right? There's no kind of, oh, don't use anything above 0.6. There's nothing like that. It's just this understanding that the closer to 0.5 you get for your probability, the more accurate the approximation is, and therefore it becomes a good approximation to use. Now, it's quite tricky in the context of the A-level to understand why we even do this. But it is a skill that's there, and it's just taught as a skill, and it's learned as a skill. And it kind of dates back to the olden days of A-level when we had to use tables of values rather than calculators to do our working for us. So those are the 2 reasons, okay? Know them, learn them, and be prepared to deploy them when you get to the exam situation. So for part B then, it says write down the mean and the variance of the normal approximation to x in terms of n and p. So, what we know about our binomial distribution is that x is distributed with a binomial distribution with n, which is the number of trials, and p representing the probability of success. The mean of this distribution, because we can calculate the mean of a binomial distribution. It's not something we do in the A-level specification, but we can calculate it, and it then becomes the mean in the normal approximation. So the mean has another name. It has E brackets x. The E stands for expected, so this is the expected value of x. So if I was to use an example, say we conducted an experiment 20 times, and the probability of success was 1/4. How many successes would you expect the average person to have? Well, you would expect them to be 1/4 of 20, which would be 5. And that's called the mean. That's the expected value, and it's the average of the distribution. And the way that we calculate it is, as I just alluded to, if we had 20 trials and a probability of 0.25, we're multiplying those 2 together to find out what you would expect to happen. So to find the mean, also known as E brackets x, we do n multiplied by p. To calculate the variance of this distribution, which we can also call var x, Okay, and these two bits of information, they're not necessary. You don't need to know that notation for the A level, but the variance is given then by NP multiplied by 1 minus P. Now, there's a long proof for this, but the proof isn't part of the A level. You can go and research it if you want to, but that's how you would calculate the variance. And it is the variance of the binomial distribution, but it does form a part of our normal approximation. So these are the two answers that we're looking for then. The mean is NP, the variance is NP 1 minus P. So now we've got a manufacturer claims that more than 55% of its batteries last for at least 15 hours of continuous use. Write down a reason why the manufacturer should not justify their claim by testing all the batteries they produce. Now, this isn't maths in a way. This is just thinking about the real life situation. And don't let an exam question like this faze you. This wants you to just consider what this question is talking about. It's talking about a manufacturer of batteries. So why wouldn't it make sense for the manufacturer why wouldn't it make sense for them to test all the batteries? And the answer is there'd be no batteries left to sell. If they tested them all, they'd be testing to destruction. Okay? The sample size is the population. It's testing to exhaustion. Okay, so there'd be no batteries left to sell. Now, there's no maths there. It's just that kind of common sense coming out of the question. So then we do get back into some maths. We've got a manufacturer claiming there are 55% of its batteries that last for at least 15 hours of continuous use. To test the claim, a random sample of 300 were tested. State the hypotheses for a one-tailed test. And again, this is all binomial, which isn't necessarily on the EPA, but it's getting into this approximation, which could be on the EPA. So, state the hypotheses. Well, we've got this distribution, X, which is binomial. We have a random sample of 300, so our N is 300, which is quite a large number, which is good for our approximation. And our probability of success is going to be 0.55, which is the 55% of batteries that the manufacturer claims. So that's our distribution. Okay? Our null hypothesis, which is what we're being asked to write down here, our null hypothesis is that, yes, the probability is 0.55. Okay? The alternate hypothesis is dependent on what the manufacturer is claiming. The manufacturer claims that more than 55%, so we've got that P is greater than 0.55. So that's it, we've stated our two hypotheses. So now we get into the normal part of this. Given that 184 of the 300 batteries lasted for at least 15 hours, use a normal approximation. Okay? So the normal approximation is this. We've got a y variable. I'm just calling it y because to make it different from the original distribution. We need mu and we need sigma squared. Okay? So mu is the mean. It's the expected value from the distribution, and it's given by n multiplied by p, which is 300 multiplied by 0.55, which is equal to, let's get the calculator out to make sure I don't get it wrong, 165. So that's the mean for my approximation. The sigma squared part, which is the variance, okay, remember sigma squared is the variance, sigma is the standard deviation, is np times 1 minus p. So it's 165 multiplied by 1 minus 0.55. So we multiply that by 0.45. That is. So we have 165 times 1.45, 74.25. So that's our variance, 74.25. So our distribution for y, our normal approximation to the binomial, has a mean of 165 and a variance of 74.25. Now I don't need the squared here because this is the variance. All right. When I use the calculator in a minute to calculate the standard deviation, I'll be using the square root of this. All right. So it says given that 184 lasted at least 15 hours of continuous use, right? So 184 out of the 300 batteries is more than you would expect, okay? You would expect 165. Our alternate hypothesis represents this greater than here, right? Those two are completely linked. So what we're actually doing here, the statistic that we're testing, we want to know what's the probability that x from the binomial distribution is greater than or equal to 184, okay? So 184 out of the 300. So we're testing x is greater than 180, greater than or equal to 184. Now, in approximating this, we are using now a continuous distribution instead of a discrete distribution. So we have to think about what's called continuity correction. So I'm just going to write a little number line over here, 182, 183, 184, 185, 186, just to kind of illustrate what we're doing here. If x is greater than or equal to 184, then we are looking at this, aren't we? X is greater than or equal to 184. We're looking at all of these numbers from 184 and above. But when we turn it into a continuous distribution, it means that there are lots of values in between 183 and 184. So what's the value that we're actually testing? Well, what we do is we use the lower bound here. In between 183 and 184, we have 183.5. So for our normal distribution, we're actually testing that y is greater than or equal to 183.5. Oh, my screen disappeared then. There we go. 183.5. Now, hopefully that makes sense, right? If you're doing 184 and above, anything between 183.5 and 184 will round to 184. So we have to include it. Anything below 183.5 will not round to 184. So now it's just a case of using the calculator. So we'll just use our normal distribution and we'll go, so I'm using the CG50. If you've got the Classways, I believe it's pretty much the same. We'll go to our normal CD. And when we're on normal CD, our lower limit is going to be this 183.5 and our upper limit we're going to set to 100,000. Our sigma value, I'm literally going to type in the square root of 74.25 using the square root button. So square root of 74.25. Now when you press equals or execute, that'll turn that into 8.6168, blah, blah, blah. Our mu value is 165, and then we can calculate this probability, and we get 0.0159, and that's to 4 decimal places. So the probability of y being greater than or equal to 183.5, which represents x being greater than or equal to 184, is this value here. Now, in order to complete the hypothesis test, we just compare this with our significance level, and we say that 0.0159 is less than 0.05, which was our 5% significance level, and so therefore we have a significant result. So our conclusions. Conclusion 1. There is sufficient evidence to reject H0. So the null hypothesis, it appears, is not correct, or at least we have evidence to show that it's not correct, which means the probability isn't 55%. So our second conclusion is that there is evidence to support the manufacturer's claim. Now, don't skimp out on these explanations, okay? You need to write the two. You need to write the mathematical conclusion, whether or not you can reject H0, but you also need to write the contextual conclusion. What does it mean for the real life problem? And that's it. We are done. So we have stated the conditions under which we can approximate a binomial using a normal. We have worked out NP and NP1 minus P. We have applied our continuity correction, and hopefully that bit made sense. I recommend writing this number line. And then we've stated our conclusions at the very bottom. So that's it. That's that question worked through.